Good day, Dr. Fakizan, and this is test one, question one. So let's get right into it. And this is the diagram that I've developed. So it has one PV bus, one slack bus, two PQ buses. So the known values for this is PV. The known values for this is V and delta. The known values for these two buses are P and Q. So the known variables uh, that excludes the power and the reactive power is the voltages V1 and V2 and delta 2. And for the unknown variables, there are 5 unknown variables. So the unknown variables here, here, and here. So with the 5 unknown variables, we are supposed to find the unknown variables through developing these equations, because P1, P3, P4, Q3, and Q4 all have values in it, and that's how we're going to develop. So before doing that, we need to develop a Y-bus admittance matrix. So to do that, we will do 1 divided by the impedances here, and you'll get a 4 by 4 Y-bus admittance matrix. And for developing the equations, we'll be using this and this equation. So we'll input the values for the Y bus admittance matrix to the equation, theta, all the values of P, Q, V, and delta. These are the flat start values right here, and developing the equation, and we input the values taken from here. So we'll be doing it for the differential of P1, differential of P3, so not the differential, the change in P1, the change in P3, change in P4, change in Q3, change in Q4. So we will be developing all these equations to write down a Jacobian matrix, and the Jacobian matrix is the differential equation in terms of the unknown variables delta 1, delta 3, delta 4, P3, and V4. So the Jacobian matrix for the first row, these are the equations that we are developing, and after including all the flat start values, you'll be getting these answers, and same goes to the other rows as well. So these are row 3 and row 4, row 5, and the end of Jacobian matrix, you will use all the answers that we got for all the rows and put it inside a matrix form and use that, and then we invert the matrix. So after inverting the matrix, we will be doing this. So we will get the change in value for delta 1, 3, 4, and V3 and V4. So the reason why we're finding the change in this is so that we can minus out the flat start values with the change in these values, and we will get the first iteration of this equation. So of this variable. So the calculation goes such as Jacobian matrix inverse times the change in P1 and until Q4, and we will get the change in the delta 1, 3, 4, and Q3 and Q4. So after getting the change in those values, which are these, we will use the flat start values minus the change of the values, and we will get the first iteration. So this is how the progress will be going for the second iteration and the third iteration. We will bring down the first iteration into the second iteration to do the calculation again. So for question 4, we will be developing a bus admittance matrix building algorithm. So for that, we need to add another branch here, so that we can actually calculate it. Without this, we cannot calculate the bus admittance matrix. So we will include the branch 0 to 1. So here is the branches, and also for 0 to 2, which is here and here, and the link between the reference bus to another bus, we will be eliminating the L bus. So after eliminating the L bus, we will be left with the 2 by 2 matrix, and we will be adding the 1 to 3 buses. So 1 to 3 will be another link, but that is not in in reference with the bus, and it will be linking towards that's the one right in the smack middle of this diagram just now. So we will add the third bus with the values, and we'll get 0.15, and then we'll get a link between bus 2 and 3. So this is also eliminating the L bus. So we will be doing 7 steps of this bus building algorithm. So we will get the final answer, which is this bus admittance right here. Sorry, bus impedance. Using that bus impedance that we got, we will be able to find the fault, to calculate the fault for the current and voltages. So that will be for question 5. We will be calculating the fault voltages in the generator buses when one of the buses gets a fault. So I choose bus 4 in this case. So for bus 4, it's a symmetrical short circuit with zero fault impedance, which means symmetrical short circuit, generally the total current of the circuit itself is generalized by getting the per unit value and times it with the base current of this whole equation. So the base current will be so before that we will be dividing, we will be getting the per unit value of the fourth bus, since the short circuit is at bus 4, so 0.215. So we'll divide and get the per unit value. We'll get the bus current, the base current value using 120 megavolt ampere divided by the voltage. We'll get the current, and for the current fault, this current will be times with the fault current per unit value to get the total fault current. And after getting the total fault current, we will be finding so we will be using this per unit value for voltage to find voltages now. So the fault impedance 0, which means that so the impedance is 0 when the fault is occurring. So per unit value is 1 for voltage, and using that we can find the voltages, the bus voltage during the fault between bus 1 and 4 and bus 2 and 4. So calculating this, and we will get these answers. So in this case the impedances are the same, so the voltages at the buses are also the same. So after this I'll be talking about how I get the question 3 to prove the calculation for the MATLAB is correct. So for the MATLAB programming, we will be inputting all the admittance value. This is all gotten from question 2, and this is the Y bus admittance matrix. So all the values are here, and then the theta values are also here, and the known variables for voltage and delta, the power injected values that are known, and defining those unknown variables with a flat start value. So for anything that has delta is 0, anything that has voltage is starting with 1. So we create a matrix for that, and this iteration is 3 iterations long. So this is how it's going to be. So the equation for power for the change in P1, the equation for P3, P4 until Q4. So the change of the change of values in P1, P3, P4, and Q3, Q4 is all done here, and we'll create a matrix for that, so we can display all that later. And this is the equations that we use for the Jacobian matrix. So for the Jacobian matrix, these are the equations that I've written down in the file. Sorry, I can't open another file here because the recording will stop. That's when
the recording will actually stop when there's another file coming in.
And we will be inputting all these values that we have defined here into this equation. So we will create a matrix for that, and it will calculate everything and put into a matrix, and then we can inverse it. So we can it will display the inverse of
the matrix as well, for the Jacobian matrix, and this will be inverse of Jacobian matrix times with the the difference in the change in values for P1, P3, P4, Q3, and Q4. So when we do that, we will be able to get the change in value for the unknown variables. So once we get the unknown variable, the change in value for unknown variables, then we can use the flat start values, which is this values right here, minus the change in values for that. So that is what we did here, the change in unknown variables. So this, we put the flat start values here, and then we will minus it off with the change in variables. So doing that, we'll get a new iteration. So we'll display these new values here. So when we run it, as you can see, so for the first iteration, we'll get the delta functions. So the delta functions is the change of P1, change of P2, P3, Q3, and Q4. And then we have the Jacobian matrix after calculating all the variables here, and the inverse of the Jacobian matrix. So the inverse of Jacobian times these values, these delta functions, you will be getting these values. These values are the change in the unknown variables. So once that happens, so we'll be doing this. So when we minus off the unknown variables with the change of values of all the unknown variables, we'll get the new iteration. So that's how we get the iteration, and the second iteration is the same as well until the third iteration. So I've already checked all these values beforehand. So after calculating all the values through handwritten, I wrote it down here, and after checking, it's all close to these values. So I think it's actually correct.
So those are the discussion for question 1, question 2, question 4, question 5, and then question 3. Question 3 had to be a separate slide because I couldn't include my video in the in that discussion, so I'm sorry for that. But that is the discussion, and I'm sorry it's a really long video because I don't think 5 minutes is enough for us to discuss all the questions. So thank you very much, and I hope this is informative. Thank you.